כיף שבאתם. אני רן, למעשה מי שהיה אמור לעמוד פה עכשיו זה ארז, שהשם שלו רשום פה, אבל לצערנו הוא לא מרגיש טוב, אז אני מחליף אותו, עשינו חפיפה מסודרת, ואני אעביר לכם את החומר.
שלחת לו מרק גוף הביתה?
ודאי, כן. אז זהו, בואו נחזיק אצבעות לארז ונקווה שיהיה בסדר, ותודה לו וגם לצוות על כל הארגון. וזהו, אז בעצם מה שאני רוצה קצת לספר לכם זה מה עושים ב-AppsFlyer, ובעיקר מה הקשר בין AppsFlyer ו-Data Science ו-Machine Learning. ואחר כך נעבור לשלושת ההרצאות שלנו. אז מה עושה AppsFlyer? AppsFlyer זו חברה שמתעסקת ב-Attribution. Mobile Attribution ליתר דיוק. מי מכיר את המושג Mobile Attribution ומבין מה זה עושה? מעולה, אני שמח שלא הרמתם מידיים, כי עכשיו אני יכול לספר. אז נניח שאתם, לא עלינו, מפתחי אפליקציות, ופיתחתם אפליקציה מדהימה, ושמתם אותה באפסטור או בפלייסטור. ועכשיו אתם רוצים שמלא אנשים יבואו ויתקינו אותה, נכון? אז אופציה מספר אחת שלכם זה לשים את זה ולהתפלל, ולחכות שאנשים יבואו וישמעו על זה ויורידו. אופציה שנייה זה ללכת ככה ולספר לחברים ולהתחנן שיורידו, ואופציה שלישית זה לפרסם. אפשר לפרסם בהרבה מאוד ערוצים שונים, פייסבוק, גוגל, יוטיוב, בתוך אפליקציות אחרות וכו'. ומסתבר שזה עובד לא רע, כל הסיפור הזה של הפרסום.
מה האופציה הרביעית של לעשות הרבה הורדות פיקטיביות ולהשיג את הדירוג הגבוה?
גם בזה אנחנו מטפלים ויש לי שקף, תודה. אז עכשיו אחרי ששילמתם, נגיד, $100 לפייסבוק, $100 לגוגל, קיבלתם הרבה מאוד הורדות, אתם רוצים לדעת איפה הכסף שלכם עשה יותר, אוקיי? איפה $100 שלכם שווים יותר. פה נכנסת AppsFlyer לתמונה, בעצם AppsFlyer עוזרת לכם למדוד את השימוש, זאת אומרת את האיכות, את האפקטיביות של הקמפיינים. איך עושים את זה? אז למעשה, בדרך כלל פרמטרים שמעניינים מי שמייצר אפליקציות, זה אחד משלושת אלה, או מספר האינסטולים, או איזה אקשנים היוזרים עשו, זאת אומרת, אחרי שהתקינו את האפליקציה, האם עשו sign-up, האם עשו מנוי, האם רכשו משהו, או בסופו של דבר revenue. שלושת הדברים האלה, למעשה AppsFlyer עוזרת למדוד, ותכף ככה נדבר איך, ויותר מעניין מה הקשר בין כל זה לבין Machine Learning. אז הדרך המסורתית שבה רוב התעשייה מדדה את הדברים האלה עד לא מזמן, זה על ידי שימוש במה שנקרא Device ID. Device ID זה משהו שיש לכל טלפון, ברגע שיוזר רואה פרסומת ולוחץ עליה, אנחנו רושמים אצלנו באיזשהו דאטאבייס כזה גדול, מה ה-Device ID של אותו טלפון. אם הוא אחר כך הולך ומתקין את האפליקציה, בתוך האפליקציה יש SDK של AppsFlyer, ה-SDK של AppsFlyer שולח לנו איזשהו איבנט, שגם באיבנט הזה יש בדיוק את אותו Device ID, ואז אנחנו פשוט עושים match, אוקיי? אם ה-Device ID של הקליק שווה ל-Device ID של האינסטול, זה אומר שקיים פה attribution. אז זאת הדרך הפשוטה והמסורתית שבה בדרך כלל attribution עובד. ולמעשה רוב התעשייה של attribution ולא רק עובדת ככה גם היום, אלא שלפני משהו כמו שנתיים, התחילו ככה מכיוון של אפל יוזמות של privacy, וביניהם גם האלימינציה של Device ID. נכון להיום זה משהו שרווח גם לא רק באפל, זה נמצא גם הרבה מאוד מקומות, ואני גם יודע שמי שהגיע מעולם הבראוזרים כבר ראה את זה בעבר, עם cookies וכו'. למעשה, היום יש פחות ופחות Device IDs שרואים, אם אנחנו מסתכלים על העולם של iOS, אז פחות מ-50%, הרבה פחות מ-50% מהדיווייסים כבר לא חושפים את ה-Device ID שלהם, ועכשיו נשאלת השאלה, איך עושים attribution? אחרי הכל זה הביזנס שלנו, וזה גם מן הסתם משהו שמשרת את הלקוחות. אז התשובה לזה בשתי מילים זה Machine Learning, ופה אנחנו נכנסים לתמונה. אז למעשה אנחנו מפתחים דרכים סטטיסטיות שבהן אנחנו יודעים לעשות attribution בצורה שהיא אגרגטיבית, זאת אומרת שהיא לא פוגעת בפרייבסי, אנחנו לא מנסים לנחש מי היוזר, זה גם לא כל כך מעניין אותנו. בדרך כלל מה שמעניין את המרקטיר, את מי שמייצר את האפליקציות, מה שמעניין זה מספרים במסות, זאת אומרת מספרים בצורה אגרגטיבית. אף אחד לא מתעניין במה השם של היוזר, או מי זה היוזר הזה הספציפי. אז למעשה אנחנו מפתחים דרכים לעשות attribution בצורה שהיא סטטיסטית, נלמדת על בסיס דאטה, ופה יש לא מעט אתגרים, ועל חלק מהם אנחנו גם נדבר היום. אני אזכיר ככה בקצרה כמה אזורים שבהם אנחנו עובדים, לא ניכנס אליהם לעומק, ואחר כך, זאת אומרת, ולאחד מהם כן נוכל להיכנס, אבל בהמשך. ככה קצת מספרים לתת לכם בכללי הבנה של איך נראה היום יום של AppsFlyer, אז למעשה אנחנו פועלים בסקייל של דאטה שהוא עצום, אני חושב שהמספרים פה הם כבר גדלו לפחות פי 2, מאז שהוכן השקף, כנראה שצריך לעדכן את זה, אבל סדר גודל שנגיד משהו כמו 100 מיליון התקנות ביום, בערך 10 מיליארד קליקים, מן הסתם לא כולם מתקנברטים. אוקיי? 100 מיליארד in-app events זה למעשה פעולות שיוזרים עושים, אני חושב שהמספר הזה הוא הרבה יותר גדול היום. ועכשיו כמה מילים קצת יותר בפירוט, על מה עושים Machine Learning/Data Science ב-AppsFlyer, ואחר כך נמשיך ונצלול לתוך אחד מהפרויקטים. אז Mobile Attribution, נקרא לזה 2.0 או 3.0 או whatever, שהוא למעשה אגרגטיבי וסטטיסטי, למעשה פועל בהרבה מאוד שיטות שונות. למעשה יש מספר use cases שונים. לפעמים אנחנו רואים צד אחד של הדאטה, לפעמים אנחנו רואים צד אחר של הדאטה, לפעמים אנחנו רואים חצי מפה וחצי מפה, ואנחנו צריכים להשלים את התמונה, ולכל אחד מה-use cases האלה יש למעשה טיפולים שונים. אז אני אעבור ככה ביעף על הדברים, אני לא אכנס לעומק, אז דברים כמו probabilistic modeling, שזה למעשה איזשהו מודל real-time, שיודע להגיד בסבירות די טובה, האם קיים attribution או לא קיים attribution, שוב, בלי להשתמש ב-device ID או דברים בסגנון הזה. hack, שזה למעשה טכניקה מאוד מאוד מעניינת, שעליה ג'ף, שיעלה אחריי, ידבר ויסביר איך למעשה עושים את זה, אז אני לא אכנס לשם. null CV modeling זה פרויקט מאוד מעניין, שלמעשה בא ומסתכל על איזה דאטה חסר, ואיך משלימים אותו. אוקיי? קורה לא מעט פעמים שחלק מהדאטה חסר. עכשיו, הלקוחות שלנו רוצים לראות את כל הדאטה. אז אנחנו למעשה מפתחים מודל שיודע להשלים בצורה כמובן סטטיסטית את הדאטה שחסר. Incrementality זה למעשה איזושהי דרך לעשות A/B טסטינג, אבל בלי device ID. אז כל מי שאי פעם עשה A/B טסטינג, זה יחסית קל כשאתם מזהים את היוזר. אוקיי? כשאפשר לזהות את היוזר זה לא בעיה, פשוט מגרילים מי נמצא בקבוצה A, מי נמצא בקבוצה B. אבל כשלא יודעים לזהות את היוזר, זאת אומרת שאין device ID ואפשר לשים עליו קוקי, זה כבר הופך לבעיה סטטיסטית מאוד מעניינת, וגם על זה אנחנו עובדים, למעשה לייצר כלים שיודעים לעשות A/B טסטינג מבלי הצורך לסמן או לצבוע את היוזרים. סקן ריקומנדרס מסוגים שונים, זאת אומרת כל מיני כלים שעוזרים למשתמשים שלנו להשתמש סקן בשתי מילים, זה כלים שאפל מייצרים כדי שניתן יהיה למדוד attribution, אלא שהכלים האלה חסרים בהם לא מעט דברים ואנחנו משלימים חלק מהפונקציונליות הזאת בכלים של Machine Learning. Creative Analytics זה מוצר מאוד מעניין שלמעשה מסתכל על תמונות או על וידאוים, מה שנקרא Creatives, אוקיי? ובודק את ההשפעה שלהם. לצורך העניין, אם יש Pickup Truck שנוסעת ועליה דרקון ורוד, זה מייצר conversion יותר טוב מאשר Pickup Truck עם דרקון כחול, אוקיי? לצורך העניין, זאת אומרת, ממש כאילו להסתכל לתוך התמונות, להסתכל לתוך הוידאוים ולהבין מה יוצר engagement יותר טוב, ובסופו של דבר כמובן לייצר אנליטיקס מעל זה. Fraud detection, כמו שהוזכר מקודם, אנחנו חיים באינטרנט ובאינטרנט יש fraud, מה לעשות, ואנחנו בעצם מייצרים כמה מוצרים בעצם שיודעים לזהות fraud בצורה אוטומטית. חלק גדול מאוד מהם מתבסס על מודלים סטטיסטיים, ספציפית מודל בייסיאני שאנחנו בנינו, אבל עוד, לא רק. ופרדיקט, שלמעשה דרך שלנו לבוא ולצפות LTV, Lifetime Value. בדרך כלל מי שמייצר קמפיין, משלם הרבה מאוד כסף על הקמפיין, והוא רוצה כמה שיותר מוקדם לדעת האם הקמפיין הזה עובד או לא עובד. אם הם יחכו 30 ימים כדי לדעת האם הקמפיין עבד או לא, אז הם שרפו הרבה מאוד כסף ב-30 ימים האלה. הם היו רוצים לדעת תוך 3 ימים האם הקמפיין הזה אפקטיבי או לא, ולשם כך אנחנו נותנים להם את הכלי הזה שנקרא Predict, שלמעשה יכול לצפות את ה-Lifetime Value של משתמשים, נניח ב-30 ימים הבאים, אבל אחרי 3 ימים בלבד. אחד מהאלמנטים המעניינים האתגרים המעניינים שאנחנו מתמודדים איתם, זה שיש לנו, כמו שאמרתי מקודם, דאטה מאוד מאוד גדול, והרבה פעמים האתגר הוא לבוא ולדעת איך לעבוד עם דאטה כל כך גדול, איך לקחת סמפל בלי לייצר בייס, מצד אחד. מצד שני, יש גם מקרים לא מעט, שבהם יש דווקא דאטה קטן, ועל המקרה הזה ג'ף הולך לדבר, ולא רק שזה דאטה קטן, הוא גם ככה unlabeled, זאת אומרת, אנחנו לא יודעים עליו הרבה. אנחנו צריכים סוג של לנחש מה הלייבל שם, אז אפשר לחשוב על זה כ-unsupervised או semi-supervised, זה לא לגמרי נופל אף אחת מהקטגוריות האלה, אבל בכל אופן זו בעיה מעניינת, וג'ף יציג אותה עוד מעט. וכמובן שאנחנו מגייסים, וזה לא כל המשרות, אבל יש לנו לא מעט משרות שפתוחות, אז אתם מוזמנים לבוא ולחפש אם זה מעניין אתכם, וזהו, ללא שהות נוספת, I give you Jeff, so Jeff is going to do this in English. You want Hebrew?
לא דיברתי על Data Science לפני, אבל הלילה הזה הוא לא יהיה הפעם הראשון.
All right, you choose your own language, maybe you just do it in Python. All right, so thank you, and Jeff, please.
Tonight we're going to speak about how to basically get something out of nothing, which sounds pretty crazy. And the situation is like, what do you do when you're trying to use the data science methodology on something where you don't have a lot of data to fit with, you don't really have labels, but you actually need a specific kind of label. Now, before we start, I'll introduce myself a little bit. Don't get too excited, by the way. This is not going to be like a talk on Eastern philosophy with all this words of nothingness and Zen. But my name's Jeffrey. I have a PhD in mathematics. I did a master's in mathematics, and at once upon a time, I used to work at Goldman Sachs when I was more of an evil banker kind of person. So what are we going to discuss? Well, we know essentially that data science is driven by business, products, solving problems for people, and we use data to do that. But what do you do in the situation where it's scarce? And what do we do where, like, the usual methods, because they don't really work so well, you know, when we set it up? Because often with a data science method, we're not really trying to, we're not often really trying to deeply understand the structure of the data in the sense of like where it's being driven from. We're using an algorithm in order to extract meaning from the data empirically. Sorry, I'm not good with the mic. So what do we do in the situation where we take our data, we apply all of these wonderful things, and we get nothing out of it or nothing useful out of it? So in the case, for example, where, let's say, we're trying to fit a data set where we don't have a specific label, right? And I would remind you, when you do clustering or one of these other, you know, unsupervised methods, you are looking for a pattern in the data. You're not looking for the specific pattern because you don't have it to look for it. So in this situation, if you want to estimate or evaluate a model, you probably need to come up with a way to at least philosophically understand how good it might be. And in that case, you would come up with a proxy data set which you at least believe is similar to the data set you're using. But whether or not this is the actual error, right, when you measure it, sort of your best case sort of way to go is to try and pick a proxy data set with the weakest possible assumptions of how they might relate. In other words, in the first case, like where the means are the same, this would be basically assuming the data sets are identical, more or less. And this would be the strongest possible assumption and something you want to avoid, all the way down to, the data sets or the error in modeling is at least similar, all the way to, well, maybe the distributions of the error between the different methods on the different data sets might be similar. And this will be the case actually where we set up our proxy data set where the idea is that the error in the modeling should be similar versus all of these other sorts of stronger assumptions we're going to make. And of course, we set up an error evaluation metric, which is just the weighted relative absolute error, which is just weighting, at least in our case, based on installs of the relative absolute error.
The two samples are the indexes the same?
Oh, sorry. Oh, sorry about that. No. So in this case over here, this is just, if you want a specific example, we would have, let's say 10 observations or campaigns or whatever you're trying to estimate. This would be the estimate of the value. This is the actual value, and that's just divided by it. You can have an issue if, of course, the value is 0, right? So you can tinker with that a bit. If you want to be really fancy, you can use a difference of means or difference of proportions test from A/B testing or from statistics if you're less markety and more mathematical.
Right here, it's the Manhattan cousin of the square.
Yes, basically, essentially. Sorry, I'm really, really terrible with the mark. It's like it's not my one. So the question we're going to ask ourselves is like, what do we do how do we sort of approach campaign performance when it's not observable? And let me explain what that means. As Ron mentioned, at AppsFlyer, we do attribution so advertisers can assess where to put their money. And by campaign performance, we'd ask ourselves, well, in this specific campaign, do people actually become paying customers, and how much money do they spend, or how much does each paying customer spend, for example? These would be things that we care about. And in general, when we have limited data, we have the day one data, right? It comes through, but the advertiser, after 1 week, wants to know how well things are going. And in some cases, that can be invisible, which I know sounds a little bit crazy, but that is the case. So what we're going to do is we're going to build a model where we use the first day to measure the first week. That's pretty standard data science stuff. But what about the ground truth? We just said that, well, the first week's invisible. We don't see it, right? For whatever various reason it is. And this is where we have a proxy data set. The proxy data set we're going to use are campaigns which, using other methods, in the case of AppsFlyer, Ron mentioned probabilistic modeling, where we can create a ground truth based on those estimates. And then this will be our sort of proxy that we use to evaluate, not to fit the model. We'll still fit the model on the data set we're trying to estimate, but that will be the data set that we use to estimate how good the model's working, to get a sense of how well it's fitting the data. That's really unfortunate. Okay, so that's very embarrassing, by the way. At least somebody could laugh a bit. That would make me feel better. Okay, so I'm going to quickly speak again about what's attribution, although Ron did bring this in. So essentially what attribution is when somebody serves an advert or clicks on an advert and then installs and then makes a sale, makes a purchase. We want to marry these things together. We want to find a way that we can attribute them, from campaign to campaign. Now, why it's complicated, again, it's since iOS 14, if you have an iPhone, you'll notice a lot of times, unless you actually directly consent to giving the data, we don't see it that. But in general, for many sources, we can still get something where your privacy is still maintained, but probabilistically we can estimate that. But there are cases where we don't even get access to the very basic data in order to do that, and that is the case of an SRN, or a self-reporting network. And this would be companies we all know like Facebook, Twitter, and Instagram. Well, I guess Instagram is Facebook, but anyway, so. Sorry?
I'm not sure Twitter is still.
You know, I haven't spoken to Elon in a while now. I'll have to give him a call and see how things are going with that. So the way we started off, like all good data scientists, right? We have a whole bunch of campaigns and we want to fit some models, but we need to create the observations, right? So one way you could do it is you can take all of your apps. For each app, you can split your campaigns into your training campaigns and your test campaigns. You can then fit the model, right? And then get your output, right? The only issues you're going to run into is one, when you create that model, you're going to create that model on the consented data, right? Sorry, on the probabilistic modeling data, and then assume that that's going to work well on your non-probabilistic model data. And we are, like you see, we're now bringing in assumption number one. The means are the same when we do that, right? And that's something we don't actually want to do. But even worse than that, because campaigns can vary quite wildly between each other, when you sort of select your training and your test, like the actual fit to the model can, first of all, be very volatile. Even if you average out, you can get quite poor results. So that doesn't work. And also, you'll see we aren't using all of the information. Now, there's something I did not mention. Even though we cannot see for the installs and the install data how to attribute it exactly, we can see which users actually made purchases. We just can't marry them to a specific advert, right? We can't do that. So what that means is at the app level overall, we could estimate that, right? We can exactly see what happens on day one and exactly see what happens over week one. So you might say naturally, all right, let's do a time series model at the app level. Let's fit a regression on that for those parameters. And then let's see how that model will run on the data itself. Now, at least here, one, we're not mixing potentially data which has probabilistic modeling on it versus data which does not, from SRNs and non-SRNs. And the other sort of strength of this is that it's on the data set itself, right? So it has a sort of purity when we do that. The only problem is that once you're at the app level, you've got so many installs and so many conversions and so much revenue occurring. I know a lot of revenue, fortunately, that it's very stable. So you're now fitting a regression on really stable data. You're going to get nice relationships. You're then going to put it on the campaigns, which are really volatile, and it's going to fit terribly. So in both cases, you'll sort of get a model that just doesn't work, right? So this idea of trying to use the thing we care about is the observation doesn't work. And this is where it becomes complicated or maybe more interesting in terms of that. So we got a little bit of inspiration from like the cinema, the movies. I don't know how much you look at Box Office Mojo. I'm sure everybody has seen a Marvel movie probably at some point. And one thing you'll have noticed if you actually looked at the data is like the first weekend, the numbers are massive, right? And then afterwards, they like drop off quite quickly. And if you've actually looked at like, they have some cinema level data as well. Like in a lot of cases, you actually see a fair amount of similarity in terms of the amount it drops off. Some cinemas might have higher attendance than others, but the sort of relative drop off has a certain similarity to that. So we started thinking, well, maybe we can think of our users and people who install in the same sort of way. The people who are the most enthusiastic about the app, well, they'll spend money like in the first day right away. And then we'll see after this like initial period of excitement will burn off, we'd have like a second phase where people maybe are less enthusiastic and have less conversions. And maybe if our data allows us, we can use this idea that the drop-off could be similar across all of the campaigns to extract a way to link week one back to day one.
Maybe you mentioned kind of saturation model.
Yes.
So but application, I'm not an expert on application, so maybe I'm wrong. Sometimes it's kind of doing badly, and then for some reason it started.
Oh, you mean you get the reverse phenomenon? You mean like instead of selling down, it sells up?
Yeah, because in first, like when you first have an application,
right,
and you're the let's say you're having a chat application, you're the only one, none of your friends has.
Right, exactly. So in the sort of methodology one can approach can actually handle both cases. It sort of doesn't really care whether things start off low and go up or start off up and go low, except if you have stuff that's wildly inconsistent, where in some regions you have like reverse phenomena. This can be a lot more complex to model. Fortunately, we haven't really seen that in most of the sort of instances. But you're right, we do have some clients, I'm not going to say who, where actually on the first day it's lower and then it does go up on the sort of daily basis. So the sort of approach we're going to take will fit that into the data. It will be baked into how we approach it. So this is, by the way, the important thing to sort of understand. So I need to focus as well, I'm afraid. So what we're going to do is this, right? We're trying to essentially model a basket of users. A campaign is a basket of users. So we're going to create a model to describe a single user. And then when we fit that model, what we would usually do is estimate quantities from that basket of users. So if we think of the two different phases from day one all the way to week one, and we think of the customer making purchases as Poisson arrivals. If you're not sort of familiar with the Poisson process, you can just think of this as, the time from the install, and this is kind of like the force of the event occurring over a very small period of time. We'll go into a tiny bit of the mathematics later, but you can just think of this as being almost analogous to like what a probability might be like over a very, very small period of time, how it works out. Now, you see, if we could estimate both that and that, there'd be nothing to do, right? Because we would have the answer. Now, we have this one over here. So the idea is that can we create a model where we can extract that from our campaign level data, find a link to link from here to here at the app level, and then from that extract out an estimate for that, and then we have both periods covered. So you can think of it as like starting off with the campaigns, projecting down into the users, finding a link from the user over the first period to the second period, and then projecting back up into the campaign data. So the way, if you want to think of this mathematically, is we have our first estimate that we're mapping to our second estimate, and then we have the sequence where we take the estimate to the model, from the next model to the second week model to the second estimate. This is exactly that. Here we can think of this as our parameters that we're estimating, and then we can set up the mathematics of it where we sort of invert the first model, link to the second model, and then project onto the final model. If you're familiar with things like encoders and transformers and that sort of thing, you'll see it's an analogous process where you transform your data set, you then map it from one space to another, and then you apply the same thing. Now, the question is this a reasonable process to do, right? Like, is this something where, like, we're going to set estimates equal to equations? And one thing we can remember is that in statistics, often when you estimate, we use something called the maximum likelihood methodology when you calculate these things, but you can also use method of moments for extracting parameters. And the one thing that we know, even though method of moments doesn't have the same sort of, benefits like UMVU and that sort of thing as the maximum likelihood methodology does, it does have the benefit that as your sample size gets very big, thanks to the law of large numbers, it will converge to the actual expectation, right? So in a sense, it's quite reasonable to set up this idea. And this is where we have our, in a sense, probability that the person converts over the first week, which is just the expectation of the binary event that it occurs, which we set equals to the estimate, which is the proportion of people who convert. And this is the thing we're actually interested in. So, as I promised you, we'll just do a little bit of math to kind of see where this model comes from. If we think back to this period where we have this, like a probability of conversion over a very, very small period over here. And to derive the equation for this, right, the probability of a conversion over the first interval, well, this is just the same thing as adding up or integrating, depending on how loose care about the mathematics. This is a bit heuristic. Please don't go crazy with the measure theory and how this thing should be defined, but you can think of this as being what's the probability that the event does not occur in the first initial period, and then just at the next little bit, it occurs. When you add this all up, it's the same thing as covering the event that the probability, covering the probability that the event occurs over that period.
0 and x.
Yeah, so over here. So it's saying like, what's the probability, like if x is, let's say 1 for day 1, that's what's the probability that the person converts over 0 to the first day, which is the same thing as adding up over. I guess you could complain a little bit that I've used x here and I should have maybe used a u or whatever, you know, for that. But anyway, nobody's perfect, right? So if you take this equation and you differentiate it, in the differentials you get a very nice formula from the exponential distribution. And this, of course, is actually a very well-known property of Poisson arrival processes, that the arrival times have an exponential distribution. And you'll see, like, for example, this lambda s over here, that will have, let's say, one value on 0, 1, and then another value on 1 to 7.
Can you repeat what does 0 stand for here? Like, what do you mean by converts to 0?
So I guess the conversion time. So conv here is the conversion time is in that interval. So here conversion is the time that the person actually will convert from being an install into a paying customer. So a very simple example is like you install the app at like midnight because you can't sleep, right? And then at 2 a.m. you pay for coins on the gaming app. And so your conversion time is, I guess, 2 over 24, right? 1 over 12 in that one over here. So it would fall within that one. Is that clear?
Yeah, but why 0?
The time that the thing starts.
Oh.
Yeah. So, okay. So if we integrate out, we get that the probability that the conversions occurs up until the end of the first day is 1 minus x negative lambda 1. We get the probability that the conversions are less than day 7 is 1 minus x minus lambda 1 minus 6 lambda 2. Here we specifically specified lambda as a daily value. That's why we have the 6 over here, because we want, as one of the things in data science, whenever you're playing around with your data, the more consistent you can make things in terms of how you can compare them from period to period, the stronger your models will be in general with that. And here is going to be our link value, right? Because we know what the lambda 1 is, because we can just set this equal to the conversion proportion on day 1 and solve for lambda 1. But to get lambda 2, we need a link to that, this k value here. And the way we do that is by projecting then from the campaigns up to the app level, okay? And then we solve for the k value at the app level because we have all of those observations, very simple mathematics. And then that pops out with our value for lambda 2. And so we can now estimate everything for that. And in terms of like, you might ask yourself, like, how does this methodology like compare, right? Well, we found that if on the data set of, I think it was something like 1,500 apps, about 3/4 of them had at least 80% campaigns with less than 20% error in the calculation, or using the error metric we referred to at the beginning, the weighted relative absolute error. It had a weighted relative absolute error of less than 10% on average for all of the apps. But one thing to remember, this is like a proxy evaluation because we're doing this on the data with probabilistic modeling, right? So this is not the same thing as the actual error, because the actual error on attributing the campaigns is impossible. I mean, only God knows that, or if you don't, depending on your beliefs, right? It's not going to be knowable at any point in the future. So we're sort of working on the basis that something should be broadly comparable in that respect. So, you know, one thing I did mention is that not just conversion, but also revenue, right? We wanted to look at the revenue per user. So how do we do that? Where's the money, right? Well, we can approach this in exactly the same way. Again, we model the user, and we then have the user starting to spend on each of the specific days. The one benefit is we already know we can already estimate what's the probability they start spending money on any given day, so we can break things up that way. All we have to do is estimate if they start spending on day 5, how much are they going to spend, and find a mapping for that. And that's exactly how we set it up. The expected revenue, given that they're paying user, will be the probability that they start spending on a given day, times by what the expected revenue is from that given day, given that they're a paying user. We can generate the formulae using the mapping we have from P1 that we get on the first day, probability of purchasing on the first day, and calculate using the formula from the Poisson arrival times. For the second part, for the revenue, this is a little bit more complicated because the revenue is going to be the number of days times by the average daily spend, okay, over the second period, which is not directly visible, right? But we're going to have the same sort of methodology where we look and say, well, maybe we can model things with the average daily spend being some multiple of the average daily spend on the first day, right? And we can extract that by trying to do it at the app level in terms of extracting that. And then with a lot of algebra, which I've spared you, so you can thank me for that, even if you, even if you wanted to see it. Yes, it's like, have you ever seen like in all the computer science textbooks, it's like, the first thing is they give you an example where like, it's like write a program to add 2 numbers together, and then the exercises are like solve the Riemann hypothesis numerically or something like that. But basically, you can extract out the same kind of formula playing the same game. It's just a little bit more complex. It's just a little bit more algebra and how you do that. If you're really that interested, we can discuss it, or you can even potentially come and work at AppsFlyer. So an incentive for you to come. So what can we take away from this? This so far, this has been like a very interesting case study, right? But you might say to yourself, it's very specific, you're using random processes to model things, maybe it doesn't quite apply, right? Now, one thing that we did find is that if in the case of conversions, we applied this transform minus log of 1 minus x, and we just apply a regression, you can actually get fairly similar results. They're a little bit worse because this model underfits a bit. Because remember, whenever you fit a model with more observations than there are parameters, well, one, you do get robustness, right? You can generalize, but also you underfit in a sense, right? Now, whether or not you're underfitting reasonably or not, this is a whole other philosophy, right? But the point is that you could have got something relatively similar just by applying this transform, right? And so what I want to point out is that by thinking about something structurally, that can help you see what your feature transformation might be. You don't necessarily have to build out the entire model and do everything. You can just try and think about how the different variables are related to each other from a structural model, which will tell you what your transformation needs to be. And what that means is that by thinking this way, you can actually do feature engineering the easy way, right? Well, okay, maybe the easy way is a bit of an overstatement, the easier way. And the other thing that, other than subject-specific knowledge to do a bit of feature engineering I want to mention, is that you'll notice when we convert those probabilities into lambdas, these things look awfully additive in the model, right? You notice we add lambda 1 and lambda 2 together, because in that space it's additive. Probabilities are not additive, right? Probability of 2 events occurring, you can't just add them together. So when you're going to take features and you're going to chuck them together in a model, look to see how you can transform them, even if it's not necessarily structural, but to transform them so that they live in the same sort of space as each other. So relative to each other, they might vary in a similar way. They might have the same kind of bounds. They might have the same properties. I don't mean transform the one into the other, because, well, then you get nothing, right? But transform them so that they can become comparable. Because even in things like regressions and in certain kinds of networks, whenever you take linear combinations, if you mix together things that are not really consistent with each other, you don't necessarily get a good result coming out of that. And on that cheery note, Thank you. We made it to the end.
I'm happy to be here. I hope that I'll manage with the mic. It's nice to be here to present to you things from my PhD, for my first year. Today I almost complete my second year of full-time PhD with Professor Gal Chechik from Bar-Ilan University. He's also famous for being the head of NVIDIA Research Israel. And I'm also a part-time consultant. Currently in my PhD, I do vision and NLP, and actually semantic segmentation, which is a non-trivial mix. However, I chose to present something that is machine learning and quite basic, quite general, because it's a common problem with a surprising solution, and actually many things, many interesting and important things to learn, I think, that I'd like to show, to present, to share. So I hope that you'll find my talk interesting and useful. If you want, you can use this QR code to open the presentation on your devices. This is the outline of my talk. Okay, so the outline of the talk, we'll talk about label shift. What is label shift? Common and problematic practices to cope with label shift, which is a problem that damages performance. The research in the area, and a surprisingly simple and effective solution that you should know. So what is label shift? So let's assume that you have a training set with this distribution of samples. As you can see, most of the samples are cats, and you have some dogs and airplanes. Label shift is quite intuitive, a case where the label shifts, and in test time you have a different label distribution. Okay?
It's not called label drift.
Maybe, maybe also label drift, but the proper term is label shift. And I want to emphasize that we are talking about a case where only the labels shift. Okay, so we assume that the label distribution shifts while the features remain the same for each label. If I train on cats, for example, then let's say it's images. So in the training I see house cats, and in the test time or production I see different house cats, but it's the same cats. It's not wild cats or the bald cats with no hair, you know, the ugly cats that look like little monsters, okay? Because this is something else. Another example let's say that you have a disease on a binary case. Okay, so we have a classifier that needs to classify if a patient is sick or not. And a case of label shift will be when, let's say that we train it at winter time, and there are a lot of people with flu. Okay, let's talk about a specific disease. And then we test it in summertime, where there are a lot less sick people. However, the symptoms are the same. If you have flu, then you get the same flu that you have at winter. You have high fever and cough, for example, okay? So this is important. And now I want to ask you to think about problems you've been working on, maybe researching, and I want to ask you if you encountered label shift. It can be binary case, multi-class, multi-label, images, text, audio. It can be also regression. For example, if you want to predict the weather, the temperature outside, and you assume that the process of getting the temperature is the same. For example, the process for making clouds and rain is the same. It just doesn't happen so much in summertime, right? So who understands that you encountered a label shift in your life, in your experience, okay. So as you can see, it's a common issue. It happens a lot.
It's the same instance, but their labeling had changed.
Not the same instances.
It's different instances?
Yeah, different, yes. Test and training and test, different instances. But the label distribution changes. The proportions or the percents of cats is different, okay? Or if it's a binary case, at winter you have 90% of being sick. Sick is let's say that it's a positive case. And at winter time, it's 10% of getting sick, okay? So just now I want to emphasize or I want you to understand that there's a mirror image of this shift, feature shift. Actually, the proper term is covariate shift. When the features change, as you can see, it's the opposite case. When the features change, but the labels per features don't. For example, we train on commercial airplanes, and we test, or in production, we get images of fire jets. So it's planes, but different types of planes, okay? And we are going to talk about the upper case, about label shift, okay? So now I have a few hidden slides that explain what happens, how label shift affects the classifier. We don't have time, so the intuition is that if you train with a lot of cats, or let's talk about the binary case, you train a classifier at winter time with a lot of sick people. Then at summertime, when you have much less sick people, then the classifier overestimates the probability of being sick, right? That's the intuition. If you're interested, you can check the hidden slides. Now, let's talk about common practices to cope with label shift, or it's called label shift adaptation. How do I adapt the classifier or the algorithm, the model, to account for the label shift, okay? To minimize the performance damage, the damage in the performance. So first option, resampling. You can resample the training set to match the label distribution of the test. For example, if this is the test now, okay, don't get confused, this is the test distribution, then you can, first of all, you can undersample the training categories that have too many samples in order to get the same distribution, or you can think about the opposite case of oversampling. For example, I want to have the same shape, the same proportions. So you can see here that I took the same, I didn't have enough dogs, for example, enough dog samples. So I oversampled and I used the same samples again and again in each epoch, for example, in each training. So if you can do this, it's quite effective. However, it requires knowing the test level distribution in advance. And it requires full training. So if you already have a model and you invested a lot of time and a lot of electricity in order to train it, and now you have a label shift in production, let's say after a few months or after something happened in the world, or seasonality, yes, for example, then you need to train everything again, resample and train everything again.
But the cheating is you have a data leakage between the test and the train.
No, you don't have a data leakage because you don't use the samples. You don't use, in those examples, in the diagrams, I didn't mean that you use the samples, only the test label distribution, only knowing how many cats, or maybe estimating how many cats you, or let's say positive cases. Let's talk about binary case. Someone tells you that now it's summertime and only 10% of the people are sick.
It's data leakage because you're
Like a distribution.
you're leaking the distribution from the test data to the train data.
So it's not like data leakage because you don't use samples from the test. You are true that you use information from the test, but it depends. I mean, you can do it. You can do it in. First of all, that's what you do in the experimental setups in papers. That's the idea. I mean, you can, as long as you don't use the labels. Okay, it depends. The idea is that you are correct that you can't use the labels themselves. If it's in production, you can invest time in maybe measuring labels of, let's say, some sample from the production data, but you can't use the samples themselves. So anyway, it's not, there is some, not leakage, but let's call it something you need to get in order to do so. And also it comes with a price. So underfitting, you can waste, I mean, it leads to wasting some of the samples. And if you do oversampling, you repeat samples again, then you need to, it can lead to memorize the samples, to overfit. Okay, so maybe another thing that is maybe even more, yes?
I wonder, where do you do the oversampling? Did you try adding a bit of noise or drift into the oversamples to see that sort of helps alleviate overfitting?
You mean augment the data or add some?
The repeated samples.
Yeah, when you do oversampling, yeah, of course you can do this, but if you have, let's say that you have 10 samples of dogs and you need to get 1,000, so it's a problem, right? Okay, so another thing that is maybe more common is to do class re-rating in the loss, okay? Or actually the proper term is importance-weighted empirical risk minimization, meaning that you add a term for each class. Add some weight for each class in the loss, and it should be the ratio between the proportion of the class in the test over the proportion of the class of each class in the training data set. Okay, so it's quite standard, and in many cases, I mean, in all the standard algorithms, you can add class weights. However, it works for algorithms that do empirical risk minimization. These are algorithms, let's say that in a nutshell, algorithms that get probabilities, okay? However, in neural nets, in deep neural nets, this impact diminishes along training. As the net trains and the performance gets up, it forgets the weights that you gave, okay? So, and if you want, there are two papers that you can check. The first one found this, and the second one tried to explain. And I want to ask you if you did this, if you had, who did this, and added weights to neural net. Okay, so if you do, I mean, remember that it's not that effective. I mean, the net eventually forgets the weights, and there are better ways of doing so.
Because you train weights that somehow diminish this your artificial weighting?
The reason is actually I mean, there is no real theory, but they gave some justifications, or they took an SVM, which is not really a net at all, but and show that it forgets. It's
in SVM is happening as well. Because in net you can consider a neural network as a learned kernel for SVM,
so it's over.
Fixed.
It's simplifications. There's not theory. They just demonstrated that this is the case for nets, for deep neural nets, and it's related to something that we'll see in next slides.
This is our homework.
What?
Our homework is to prove.
Yes, the homework is to. Yeah. And also, this method requires the same knowledge. As we talked before, you need to know the test level distribution, and it requires full training, so you can't do it. If you have a net that is already trained, you need to train everything again. By the way, in logistic regression, it works, okay? So in very simple algorithms, it works, but maybe not in boosted trees and in nets, etc. Okay, so you need to check it before you use it. Okay, so now what about the research in the field? So 20 years ago, a Canadian named Sarin, maybe, I don't know how to pronounce it, developed an algorithm, an EM, for label shift adaptation. So what's EM? Expectation maximization. It's a broad parameter estimation algorithm. And he developed it, he developed an EM for label shift adaptation. This EMs in general don't need ground truth, okay? They estimate the parameters without the ground truth. You cannot always use them, but when you can, there are good reasons for doing so. So, the big green thing, the good news is that it works in test time. So you don't need, and it does estimation and adaptation. You don't need to know the label shift in advance. If you have a fixed classifier that you already trained, it's okay. Even if you don't know the test label distribution, you use EM on the test dataset without knowing the labels. And this method estimates the label distribution and adapts at the same time. Another thing that is wonderful, it's super effective and it's super easy, and it's 3 lines, iterations over 3 lines of NumPy or Torch lines. Yeah, okay, so it's very, very, very easy. However, it requires, that there's always a but somewhere. So here is so it requires a calibrated classifier. What does it mean? It means that we need the outputs of the classifier to be probabilities. If, for example, you have a classifier for sick people, and the classifier says 0.7, if it's calibrated, it means that in 70% of the times of the patients, the predictions, it will be correct, and in 30% of the predictions, it will be wrong. If it's not the case, if it's more than that or less than that, then it's uncalibrated, okay? So I hope that it's clear. And now I want to ask you another question. Who knows that neural nets deep neural nets with cross entropy loss give you calibrated probabilities. So if, you can raise your hand. Okay, so I also...
No, max is not probabilities.
With a cross entropy loss?
Still not probabilities, as I know.
Okay, so I also thought that it might be, but I suspected it is not, and nobody really knew, and it was very vague. Until I encountered this paper from 5 years ago, with thousands of citations, as you can see, that demonstrated that deep neural nets sacrificed calibration for performance. As they get better at the performance, they get worse in calibration. And even with cross entropy, it doesn't matter. Of course, they tried it with the cross entropy loss, which is if you take logistic regression with a softmax, which is logistic regression, right? Then you get probabilities. So if you take one neuron and nothing else, then you get probabilities. But if you take a lot of them, we don't know how to describe it, and we don't know why, but it doesn't work. And this is very important. You should remember this. Now, unfortunately for us, Alexandari et al., a group from Stanford, came with a simple idea. Okay, so they calibrate neural nets, then use the same EM that was developed 20 years ago. Okay? And this is the current state of the art. It's the best technique for level shift adaptation. Calibration is very easy. It's like logistic regression. So you take a neural net, or any classifier you want, but let's talk about neural nets. They are miscalibrated. They are not calibrated. So calibrate them with another little data set. There are, little things to do, to care about, but it's pretty simple. Then use the EM, and that's it. So it works on deep nets. However, something that is not red, it's not orange, but it's strange. It's a technique for neural nets that is not a neural net, or it's a technique for deep learning that is not deep learning. It's something external and quite simplistic, which is interesting. When we found it, me and my advisor and another doctor from NVIDIA who works with me, we thought, okay, so maybe we should invest time and try to do label shift adaptation in a neural way, with neural nets. We call it deep label shift, DLS. And that's what we did. So this is the experimental setup of all those papers that I talked about, that I mentioned. Even the paper from 20 years ago. You train on a uniform distribution of labels, and then you test on a label shift. The test label distribution is sampled from a Dirichlet function, Dirichlet distribution, with some alpha that controls the shape of the distribution, or if you want, the shape of the strength of the label shift. Okay? If you have a higher alpha, then you have actually a weaker label shift. You have something that is more uniform. I can show you. Okay? If you have higher alpha, then it's more uniform. It's weaker shift. Y-axis is the test error, so lower is better. And these are results. I'm going to show you results on CIFAR 100, which is 100 classes. More interesting than 3, right? And actually, those results are, I calculated those results, I got those results after I found a huge bug in the state-of-the-art code. And those people from Stanford, we informed them, we together in response for a paper, and they apologized. And it corrupted a third of the results in the paper. Anyway, I corrected it, and those are the results. So lower is better. The worst, which is high, is the unadapted case. Blue is my model, DLS. Orange is my model with EM, infused inside the net, actually. It's a differentiable, EM is a differentiable, I mean, those 3 lines of code that I told you about are differentiable, so I could add them to the net. And actually, the easiest, I mean, the state of the art, which is the simplest thing, just calibration plus EM, is the best, you know, they are very close, I mean, my model and EM, but if you have a complex model plus EM reaches results that are near just EM and calibration, which is also very simple, then of course that you should prefer, you should go for the simpler solution. So after half a year of research, and we tried a lot of things because our main reason for doing so, we believed that the net could learn to adapt also the classifier. That's the method with EM didn't. They assumed that the classifier is fixed. We don't actually know until now, until this day, we don't really know why it didn't work, but after some time we just let it go and continue to other projects. And this is the summary. So first point is that sometimes 3 lines of code can beat a richer model, and it happens sometimes. Sometimes less is more. Actually, if those 3 lines or whatever, if the easy solution perfectly fits the problem that you want to solve, which was the case, apparently. Also, there's a lot to learn, even in failures. So you saw that I didn't succeed, we didn't succeed, but there are a lot of lessons to share and a lot more that I didn't have time to share. Also, deep nets are uncalibrated, so you need to remember this. It's a very important thing to remember, to understand that when a net gives you 0.65, it doesn't mean that it happens, that it's correct in 65%, okay? So if you are working on medical or autonomous vehicles or models that need probabilities like that model, EM, then you need to do calibration, and the good part is that calibration is very easy to do. And for label shift, use calibration plus EM.
Can you repeat the formal definition of calibration?
I didn't talk about how to do the calibration. I can.
The definition, just
the definition.
the formula.
Adding another, let's say, a thin model that makes sure that. Did you hear what he asked? Okay.
What is the definition of calibration?
Yeah. What is the definition of calibration? So, calibration is a process after which you get a classifier that is calibrated. You start with a classifier that is uncalibrated. Okay, meaning that eventually when the model or the final model gives you a score, This score is probability.
So, okay. So instead you have for binary qualification, instead you have a true or false, you have 60% true, 60% false, 40% false.
No, because a normal classifier can also give you scores, but sometimes the scores are uncalibrated. They don't accurately represent probabilities. That's the point.
But that doesn't. Like if you choose proba.
Yes, predict proba. Yes, you do. Yes, exactly. If you do predict proba, it gives you a number, but it's not the accurate probability.
All of us had been there.
Anyway, so this is it. If you need help, you have questions about calibration, label shift, about vision, NLP, time series, data science in general, machine learning, then you can approach me. I'm also a consultant and a freelancer. If you want to ask about my PhD, my research, anything at all, so feel free. This will take you to my LinkedIn, and you can also find me, right, Oz Livne, and that's it. Thank you. Do you want to have a question session? Or?
Can I ask one question?
Yeah.
I think you optimized here for not for probability, for accuracy. What happens if you optimize for F1 or for some other metrics that, or we can say other fancy metrics instead of
optimizing? When I talked about, for example, doing EM on CIFAR 100, I optimized the cross entropy loss. So it's not accuracy, it's not metrics that are intuitive. It's actually the measure of the probability, the predicted probability, the distance between the predicted probability distribution and the ground truth distribution.
So it's kind of a...
But you do it all the time.
What will happen if you will optimize to some fancier metrics?
Yeah, because
what we all mean.
But you're not just differentiable. I mean,
yes.
It's, let's say you take what is the cross entropy. You can consider it as two metric between two measures, basically.
It's a measure between two distributions.
Two distributions. So basically, it's a metric of measures. And if you did the measure theory, you do it all the time.
Yes, and accuracy or other
metric and maybe
they are not differentiable. So you can't. This is why we do it. I mean, all of the world, when they train neural nets or other models, for example, in CatBoost, you also use cross entropy loss, and you optimize for cross entropy in order to. What you really want to get is that the predicted probability distribution will match that of the ground truth. So when the classifier tells you a number, it's the probability of getting this. This is what it's supposed to do.
In the cross entropy, you have some kind of calculation trick, so you can calculate it way faster than if you do it like L2 norm. So you have an advantage. If you're taking other norms, you might lose this advantage, and maybe you would be more accurate, but computationally wise, you would be.
It doesn't originate in computation efficiency. If you do L1 or L2 or other measures, it's not probabilistically. I mean, it's not the right way to do parameter estimation. There's a theory. I mean, not for neural networks, but for other algorithms, you do empirical risk minimization by minimizing, by getting the probabilities closer, okay? This is how you do it.
Sympathetically, yes.
Question, you can approach me if you want to ask other questions, or you can read the hidden slides and find out more stuff. And thank you.
I'm Alex from Anodot, and if you don't know, Anodot does autonomous business monitoring and anomaly detection at large scale. as well as cloud cost optimization, but I'm not going to cover this topic today. So how large the scale? This is actually the screenshot from our monitoring system, and we are monitoring Anodot with Anodot, so like eating our own dog food. And you can see here 500 million of real-time metrics with millions of anomalies, and we are reducing actually millions of anomalies by 2 orders of magnitude to correlated anomalies. And the correlation process is the process we are going to cover today. In terms of data points, you can think about like 1 minute roll-up metric sends at least 1,000 data points daily. So like do your math about the data in the system. Some of our customers, probably you like know most of them, and AppsFlyer is not here for some strange reason. So what I'm going to cover today, we will talk about correlation process and the building blocks of correlation in our system. So we will discuss basically each building blocks here and spend most of our time today on LSH. Like most of our time is like 5 minutes, just to understand how things work and how you can create your own LSH model in 5 lines of code. Two slides. So yeah, okay. So we will discuss how our system works. We will talk about correlation algorithms. The correlation algorithms different correlation algorithms we are using to correlate real-time anomalies in our system. The difference about online process and offline process, and what actually happens during the online process and offline process. And we'll talk about LSH and the system architecture we have here. So how are we discovering anomalies in Anodot? So basically, we are doing it in 5 steps. We are collecting data from our customers, from API calls or real database connections. We are creating baseline for each metric, ingest it into the system in real time to detect the anomalies. All the detected anomalies correlated into some correlation groups, right? And user can create alert, can define like its own alert on each anomaly. And once the anomaly is sent to the final user, the alert sent to final user, he can give us a feedback about each specific alert to tune it and basically to improve it. Okay, like, is it clear, like this process? Okay. Okay. So here you can see how it works for a single metric, single metric process. So the blue line is the number of active users, for example. In the beginning, you can see the baseline is very wide. We don't really understand what's going on in the data. After a few periods of time, it's like daily periods. Like if after 2 or 3 days, you can see the baseline is much more improved. And after about a week of data or 2 weeks of data, you can see we discovered the weekly seasonality, and the baseline is almost invisible. It's very close to the real data, right? Okay, so, and the second example is actual anomaly in the system. So you can see very simple, right? Everything inside the baseline is the regular data, outside the baseline is the anomaly. So in the second example, you can see some anomaly, and it's red, which means it's anomaly in the system, and this one of the anomalies we will send to our customer. So why do we need to correlate at all? Like, why are you not saying, okay, you can't find anomaly, just send me the anomaly and you want to see it? So basically we have 2 good reasons to correlate. One of the reasons is for root cause analysis. Like, it sounds funny, but yeah. Correlation not means root cause analysis, but to create root cause analysis, I need correlation. Okay, I need to create some anomaly groups to understand what's going on inside. And the second reason, basically, we have a lot of anomalies in our system, and probably you can just receive all the anomalies we have in the system. Again, I will give you examples for both. So this is the first example. You can see I discovered some anomaly in payments, I think, and another anomaly in API errors. Okay, so I have some spike in API errors and some drop in payments. So I want to create a single anomaly group and to analyze it and understand, okay, the API is not working, which is why I'm not receiving like enough payments. And the second reason, which is also from one of our customers, you can see here like about 1.5 million of metrics, actually about 4 million of metrics, sorry. 4 million of metrics with thousands of anomalies and just a few alerts it's about 1 day of data, right? 1 day of data, you have 4 million real-time metrics and thousands of alerts, thousands of anomalies. So before using Anodot, the same customer worked with 30,000 alerts daily. So it's just insane, like NOC can't respond to all the alerts we're receiving. And basically using correlation first and fine-tuned alert configuration, we created a situation of like under 50 alerts per day, which is like suitable for the customer. So, hey, okay. So how the magic works? So we have like 3 main algorithms working in our system, one of which is graph correlation, the second one is name correlation and abnormal correlation. I will explain the internals of each one of those and we'll discuss some pros and cons. So graph correlation is pretty like straightforward. We can, it's basically just regex on top of metric configuration, or we can discover it from system configuration. Like if customer creates some alert on multiple metrics, we can assume you have some correlation between metrics, okay? It should be some reason like customer wants to see it.
Is graph learnable?
It's, we are learning from the configurations like metadata, right? It's not real data.
But you can apply like some kind of transformers that can control your graph or the data.
Yes. Okay. But again, like mostly, like in most of the cases, it's about regexes and some user configuration. Yeah, so it can be explicitly or implicitly. And again, we are assuming like multiple metrics coming from the same data source are correlated. You can think about it as like multiple group bys on the same tabular data. So you will find anomaly on each group by, probably, right? But all the group bys are coming from the same anomaly. So probably you have one large anomaly on the system and just able to see it in different slices by different group bys. The second and like a little more interesting, like, okay. And the second more interesting one is the name correlation. You can see it's like TF-IDF-ish. Probably the good part about it, it's like metadata based. You don't need to understand what's going inside the metric. You don't understand like to analyze the metric behavior, right? And it's very like explainable to the customer, pretty easy like to understand. Okay, if you are interested in shoes sales in London, probably you are interested in shoe sales in Berlin or whatever. Again, it's like toy example. In real system, it can be tens of tokens, and like total dictionary size is tens of thousands of tokens. Hence, some dimensionality reduction is applied here to have a single like fixed vector size as output. Okay, so it's like one of the vectors we are using. In our, and probably more interesting one is abnormal correlation, and abnormal correlation is actually used on understanding the data behavior. So you are assuming if your metric behaves the same way and basically fails the same way, yes, you have the same anomalies during the same periods of time, those metrics should be somehow related, okay? And yeah. So we can compare it and we can understand what's going on. The good part about it, again, comes from the real behavior of the metric. The less good part about it, it's actually you have some calculation here, and it's also not suitable for cold start, obviously, because if you don't have history, you can't calculate it. And like another problematic example is, for example, if you have one metric reporting for a few months and another metric reporting for just a few days, and you have perfectly matching anomalies on both, but still the cosine similarity will be pretty large. Right? So you need to solve it somehow by cutting it or whatever. Okay, so we have a few correlation methods here, and we have a few requirements for the system. So obviously we can't load all our vectors into the memory and use it like real time. And we need to support a real time, like to compare any ongoing anomalies real time. So once I have a new anomaly, I want to understand to which anomaly group I need to assign it. So basically, any new anomaly comes into the system, I will need to compare it to thousands of anomalies I have in the system now, right? So we can't run it on a real time. We can't do those calculations real time. We need some offline process, and the offline process we're going to discuss now. Yes, LSH. So LSH is locality sensitive hashing, and it's pretty old algorithm for approximation. So basically, we don't want to compare the real vectors. We want to find the good candidates. Okay, we are creating a very small model. It's basically like a tiny model in terms of, millions of metrics we're serving, and we are finding like tens or maybe hundreds of candidates with very high recall and low precision. Okay, so the idea is I will have like during the real time, I want to query my model and ask like please find like any good candidates for this specific anomaly, and it will return me some models. I will check the distances, and we will review all the prods like in a few minutes. Okay, so we are starting from we are starting the LSH from some like assuming this your like vector space. We will start the calculation from randomizing some hyperspaces. Okay, and giving some signature for each vector we have in the system. So, for example, the red one will have signature of 101 just because it's on the one side of H1, like hyperspace 1, 0 side of H2, and 1 side of H3. Yes, and we will have like, once we need to compare the red vector, like any of red vectors with something, we will check only our red vectors. So if I will have like anomaly on red vector, I will check only our two vectors. I don't need to compare it to all our vectors I have in the system. Okay, and another trick we are doing here, we're just converting the binary to decimal just to make it easier to work for us. Basically, so it's 101 is 5 now. Okay. What's the good thing about LSH is a small number of hyperparameters. Basically, you have only 2 hyperparameters in LSH. One of those is the number of hyperspaces your hyperplanes you are hyperplanes you are randomizing, or complexity of the model, and the second one is the number of LSH models you are randomizing. Okay, so we will need more than one LSH model, but let's check it in the next slide. No. Okay, so how can we choose the number of hyperplanes to randomize in LSH? Basically, just to have some intuition about it, let's think about extreme cases. So one of the extreme cases, I have just one hyperplane in the model. Okay, you understand, like worst case, I will have all my vectors in the same bucket, and it's absolutely not useful. But again, this model will be very small and very easy to calculate, since I need to compare just to one hyperspace. But on online phase, it will be almost not useful because it will provide me a lot of candidates and a lot of not good candidates. Our extreme example, like a lot of hyperplanes and average bucket size is like 0 to 1, which is also not useful because you can't find any good candidates if you have just one vector in the bucket. Okay, so you want to be somewhere in the middle, and basically you will think like how many compares I want to run during my online phase, and it will affect the design of your system. Okay.
Chosen randomly, or you have some kind of...
No, I have optimization. I'm basically optimizing it per customer. So I'm choosing the number of vectors per customer. Also, I have some maximum number of hyperplanes in the model. I'm using 16. Just if you remember the trick for binary to decimal, so I want to keep it under 2 bytes of data. Okay.
Can you use some kind of a line sweep algorithm to optimize it?
Depends. You can. You have a lot of works about like optimizing hyperparameters for LSH, but you have another hyperparameter I'm not covered yet. Basically, the second hyperparameter. Second hyperparameter is the number of LSH models you are working with, and you can ask me why do you need like more than one model at all? Okay. So yes, you need more than one model because LSH algorithm is absolutely random. And it can put almost identical vectors into separate buckets, right? Because you have zero distance measurement here, just randomly putting some hyperplanes. Okay, so adding more LSH models will improve your system recall. Again, in our system, I'm usually using about like 10 models. I see like at 10 models, I have 99.5% of recall. So it's good for me because again, I have like different correlation methods, like covering each other. So it's fine. Like I will have like 100% all the time. But again, it's something to think about. Like maybe you will need 20, maybe 5 is good enough for you. Okay, so here I'm just showing how it works. So I'm choosing like 3 different LSH models for the same vector space, right? And the diamond vector I used before, here it's 5 in one model, 2 in another model, and 0 in the third model. Okay, and 5 to 0 actually, and 5 to 0 actually is the signature of this vector. Okay, this is the LSH signature. Basically, LSH signature 5 to 0 for this vector, and just in case it's the only vector in this vector space having this signature. Okay, you don't have like any other vector with the same signature in this vector space. Yeah.
What's the difference between having a lot of models and having a lot of vectors?
Having a lot of models and having a lot of vectors. You have a difference because you're changing the both complexity of calculation of the model because you will need to compare each your vector to multiple hyperspaces. Also, like you should assume some distribution inside the vector space, right? So just randomizing multiple times different vectors and sometimes having the same vectors in the same bucket is better than like randomizing much more vectors and you don't have cases with the same vectors in different buckets, right? Again, at this step, we are improving our recall, right? It just to overcome the randomness of LSH.
Do you compare against the same identity in each of the models, or only the ones with the same signature?
I have it in the next slide. Like you're asking, like in inference time, how it works. Yeah, next slide I will cover it. So what's LSH complexity? Basically, I will skip this slide, but the fast calculation is it should be about O log n of number of vectors you are working, and in most of the cases, the answer is I don't care because again, anything calculated during the offline phase is just not sensitive enough for us, right? You care about the online phase and how fast you can compare your vectors and not about how long the offline process running every night is running. But it should be about O log n if you are assuming the number of hyperplanes about log n, which is pretty like good assumption because you can think about log of 100 million is about 8. I'm talking about 10 hyperplanes per model, so it's fine. Okay. Obviously, it's much better than any index or brute force analysis. So we discussed how to build the LSH model during the offline phase, but how we're actually going to use it in our system. So assuming you created some LSH model and you have a lot of vectors having LSH signature, in our case, we took just 3 LSH models, so we have signature of length of 3 for each vector in your, you have like sort of bag of vectors, and you have some query vector of 5 to 0. So now you're going to choose what is the candidates actually from this bag of vectors. And the candidates are any vectors having 5 at the first position, right, 2 at the second position, or 0 at the last position. Okay, is it clear? Okay.
But if you have a 10, you are still choosing just one? Or?
No, and you will check each bug, like each model separately, because like the first position coming from the same LSH model, the second position coming from the same LSH model, and from the third position. So you're checking it. I want to find vectors having shared bucket in at least one LSH model. Okay. Okay. So in this case, I found just 4 candidates, and for those 4 candidates, I'm going to measure the actual distance. So I'm measuring like cosine distance for those 4 vectors and finding 2 good candidates. Okay, you can take it as 100% recall and 50% precision, but it's just funny, right? It's you will work with like single-digit precision with LSH models usually, sometimes much less. The precision is very like low usually, but the recall is very high. Again, we are choosing it for a high recall, not for a good precision. Okay, how the data pipeline works in our case, we are just collecting all the samples of the data for the previous period of time, generating all the anomalies and taking the names for name similarity and anomalies for abnormal similarity, storing our model and running the LSH process. We are running in Spark jobs. Basically, it's on very like heavy data, and vectors like. Again, you will need to store both vectors and signatures because you need signatures to find good candidates, right? And you will need the vectors to find any actual match, right? So we will need both vectors and signatures. We are storing in Cassandra for all our vectors. And yeah, it works like pretty good with some cache in the middle. So during the online phase, we are catching any new anomalies in the system and looking for good candidates using LSH, comparing the actual vectors with cosine similarity and taking anything over the threshold. So it will add actually the anomaly into the anomaly graph or create a new anomaly group from a single anomaly if nothing else found. Okay. Some optimizations to think about. So as I explained, we are using multiple correlation methods, but basically we are taking only the first match. Okay, so if the metric is matched using name correlation, we are not going to check abnormal. Okay, we want to return like the result as fast as we can. As well as more promising models first, it can be more statistically promising model, or it can be just the cheapest one to calculate, right? So if it's very fast to calculate regex, probably I will just check regex first. Okay, and as well as loading the vectors on demand and saving in cache, because again, you don't want in production system to load all the vectors into the memory. And in our like interesting part is comparing the smaller graph to the bigger one, because usually it's much faster to find the matches. This is our setup basically. So you can see here it comes from the like data sources from APIs or database events. On the right side, you have all the offline part with data lake and Hive Spark jobs calculating the vectors. On the left side, you can see the online grouper, which actually will create the correlation graph and combine all the instances. And in the middle is the anomaly detection process, which sends any new anomaly into the stream grouper consumes to create the correlation graph. Yeah, I think I covered it more or less. It's less interesting, but we did some changes. We checked like how it works with Hive, how it works with Spark. With Spark, it works much better. PySpark, obviously. And also, like if you can compress your data, it also like works much faster because in large vector space, like you are spending more time on just loading the data than on the actual calculations. So it can be helpful for someone, maybe. And if, sorry. So yeah, again, we covered all the building blocks. Probably you understand like how to use LSH. If it's anything I want you to take home is if you have some big data projects, try to use LSH and be able to to optimize it for your needs, to tune it somehow and find the best hyperparameters matching your case. Thank you.
The hyperplane claims a technique for other types of correlations.
What do you mean?
It's not on like basically what you did here is you cluster anomalies.
Anomaly, yeah.
But, I think it's only the tip of the iceberg. I think you can use this correlation to way more instance, especially in big data, that you can do the full Pearson. And even if you could, it's totally unstable. And I have a hunch that your method is way more stable.
It can be. We in our case we just can't analyze the data samples this way because we have just a lot of data samples. The anomalies is just very small amount of the.
It's one use case, but I have a hunch. Maybe I'm wrong, and someone tell me that it's useless and it will be. But I have a hunch that you can use it to other types of when you want to find. I want to say correlation. Let's say association between a instance group.
It's basically it's not correlation. It's any approximation, any distance approximation. Distance approximation problem you have, you can use it.
Correlation. So it won't be a correlation, but you can consider it an association between some groups. And in my data science experience, this is something that you use it all the time. Association. So I believe that taking this technique with the same code that you wrote to other use cases might be interesting.
Or it's used for other use cases. LSH is hashing. It's a smart way to hash.
Yeah, to hash. It's a geometric hashing.
Yeah. The first time I used LSH, I used it, I think, for NLP problems, just to, for approximation of distances between texts or something like that. Like, you have a lot of use cases for LSH. Any other questions? Thank you.